Hello. Hello. Okay, do I have, okay. Hello, Jocelyn. Hello, Gabriella. Hello, Sydney. Okay, we got a smile. You're ahead of me. That's someone's had coffee. Okay. Hello, Melanie. Hello, Effie. Hello, Sinead. Oh, Sinead. Yeah, we need to talk about the logins, but okay, or I'm aware of the two. All right, anyway. Good morning, good morning. Who else is that? Good morning, Norma. Okay, chat. Why? And hold on. Oh, speaking of chat, there's something in chat. Who else is in chat? Good morning, Angelina. Good morning, Jean. Good morning, Effie. Double. Good morning, Jocelyn. Double. Good morning, Melanie. Double. Good morning, Sydney. Double. Good morning, Lunar. Where's Lunar? Okay. Good morning, Sinead. Double. Good morning, Zebo. Good morning, Gabriella. Double. And prom. Good morning, Genesis. And smile. I think there's a piece. Yeah. There should be a portal for early morning smile. Okay. Um, good morning, Nadine. I saw it. Okay. Good morning, Teresa. Good morning, Chanel. Good morning, Norma. Thank you. Double. Good morning, Joshua. Good morning. Oh, that's me. Okay. Hopefully you see. Oh, oh. Oh, okay. I see the direct chat. Oh, good morning, Rebecca. Okay, and we'll start in a second. I see the direct chat. There's only one, so if you're direct chat, you know you are. Wait. Okay. Oh, sorry. Okay, we'll move on. But direct chat person got log back in under the old. Well, okay. I think I get it. Wait, hold on. Hold on. Yeah. Oh, okay. Great. Thank you. Sorry to be public. Okay. Great. And you could put in for points for compose for. Okay. Thank you. But put in for points for closing that conversational loop. I'm glad that that's one load off my mind. Another load that really is on my mind. I hope you all see in the chat. I'm not going to dwell on it because I don't want to waste more of your time like talking about what there's nothing to say about. But just know that I know, and believe me, it's getting me down too. Not as much as you, I'm sure. But and it's like even awkward to hold class when there's that elephant in the room. I know, but it's better than not holding class for a thousand reasons. For a thousand reasons. So, um, oh wait, someone else is okay. Okay, so we're gonna just start. But one other announcement, and if you don't know what I'm talking about, you can check. If you just logged in, I'm gonna repeat what's in the. I mean, I'm gonna copy and paste the chat again, just so everybody can see it, so we can move on. Yeah, but the class material. Someone else here. Someone else is here. It only took me like 2 months of this class to understand that there were two different Gabriellas. No, it didn't. It took me a couple of weeks, um, but I'm oh, but okay. And I know that they are different. I know you're different. Just like I know my two sons are different, except when they act exactly the same. Okay. Um, Yeah, okay, so now that everybody's here, I'm gonna repeat. Well, I'm gonna put something in the chat again, a long paragraph of apology. If you already saw it, you already saw it. But now minor apology, not really apology, minor acknowledgement. Or just raise your electronic hand or say if you saw my note in the stream at the end of Wednesday of last week. Like I put a sort of an unusual thing in the stream, in the Google stream, about directing your attention to the class notes for the. Thank you, Gabriella C. Thank you, Teresa S. Great. Thank you, Melanie C. Okay, awesome. I love that. Okay. So good. So we're not going to dwell on that, but that's important. I mean, especially for the final exam, presumably, and because the material is now, as you notice, it's gotten thicker and thicker, and I'm trying to move through it sort of faster and faster on the theory that when you really, it's like playing piano, scales or anything else. Like if you really spend the time on the fundamentals, then the applications become more accessible to you. Like I don't like the idea is that you get faster and faster at seeing more and more complicated applications of these physics fundamentals. So the applications are getting thicker now, in particular, lab 5, for which I believe you still have a formal report due. I think, correct me if that's not the case. Um, I mean, it's both mathematically and conceptually thick, in my judgment. So, just wanted to make sure, yes, the problem that we did last Wednesday that shows you how to analyze friction, how to take into account friction in a problem. I, as some, I sort of rushed the end. Someone caught one error, which was terrific, and they got points for that. But then I said I'll sort of complete the problem for you in a PDF, which I did. But again, just to make clear, like even as I was completing that problem, I realized, oh wow, yeah, this is a thick problem. Like this requires an extensive solution. And I went back and sort of then caught one other type of, one other careless thing. So you should take that PDF seriously, more than usual because it's extensive, it's thick, and because a lot of it is not in the recording. Okay, but you saw that, so okay. And now I'm going to still use the knowledge of it today. Like the whole principle of last Wednesday was looking at how friction works, looking at how friction works. Oh, and looking at how friction works. One big takeaway that is meant to come from last Wednesday is that friction is always, the frictional force on an object is always directly proportional to the normal force acting on that object. So, and they're always on two different axes. Like by definition, the direction of the friction force is perpendicular to the direction of the normal force. The more you go like this with two surfaces, the harder they are to go like this. So you always need to know how hard they're doing this in order to know how hard they're doing that. Therefore, one needs to calculate the normal force first, and one needs to realize that the normal force needs literally to be calculated it by virtue of F net equals ma. The normal force cannot be memorized. I mean, there literally is no formula to memorize for what the normal force is in a situation other than F net equals ma. So you always have to do the normal force first. And this is why, and I'll stop in a second, I'll go to, this is why the way to analyze, well, this is one of the reasons that the way to analyze problems is we draw a system schema, we draw a bunch of pure forces, then we break those forces up into components lying along perpendicular axes, and then we analyze we expand F net equals ma individually, independently, one at a time along each axis, one at a time, so we can get all the forces acting on that axis and then move to the next axis. And as a pro tip or as a strategy, 9 times out of 10, the idea is to analyze first the axis that contains the normal force so that you get that information and then apply it to the axis of acceleration where the friction is acting. Okay, that's sort of what was meant to be the conceptual or a big part of the conceptual takeaway of last Wednesday. But you see, it got thick once there was an angle involved, which was the other purpose of that problem. So the problem introduced friction, but it also introduced an angle, which is what both of those are what I want to emphasize today. It got thick because there was an angle involved. You had this you had a box that we were pushing along a horizontal surface. We were pushing the box at an angle. So our push we thought was helping the box accelerate along the horizontal surface. But since we were pushing at an angle, as we tried to push the box to help it move along the table, we were actually increasing the normal force on the box. Like we were pushing like this. So there's a horizontal component that seemed to be contributing to success in accelerating the box. However, since we were pushing at an angle, we're also not only pushing over, but we're also pushing down. By pushing down, we're squeezing the box to the table more. That's increasing the friction war. So there's this weird paradox of that problem conceptually and mathematically that the more we try to help the box, the more we're also fighting against ourselves. And that's realistic. That like life, hello. So the equations become very interdependent. They're like simultaneous equations. So okay, so welcome to the life of physics, but we nonetheless we're able, you have two unknowns, but you have two equations, so they're solvable. So we did, or I did in the PDF. We're going to see the same. So that's the point, is that the laws of physics act independently along each axis, but just like with big old duck, or just like with kinematics problems, the laws of physics act along two axes independently yet simultaneously. So then there's a connection between the information, which is time in the case of like your exam problem or the peachy problem or the big old duck problem, etc. So here the connection is friction. Friction is what connects the consequences of one axis to another. Now okay, so we're going to see that again right now, and you've already seen it in lab 5. Everything I'm going to do now is like directly about lab 5. Lab 5 involves friction and involves an angle. Okay, what's the catch? What's the sophistication of lab 5? That now the angle is is the angle of the plane. We've now taken the actual surface that the object, we've taken the surface that the object is on, and we've tilted that surface. So the object is actually accelerating along a non-horizontal surface. And the non-horizontal surface has friction. So the ultimate punchline of what has to happen today is like right on the board right now. I'm going to back up and like the ultimate punchline that throws people at first, and then they just memorize or something, is that in fact we're going to end up breaking up gravity in this problem. And we've never done that before. I mean, you have because you've been in the lab, but you had never done that before you were in the lab. So the trickiness is like how to break up is why and how to break up gravity and then throw friction and all that. So the punchline, I think, is understanding how the top picture actually leads necessarily to the bottom picture. Like I think the punchline of the whole thing is how you know that the given angle from the lab. Sorry, let me just say this clearly in case you've never. If you tilt a surface at some theta where theta is measured with respect to the horizontal, measured from the horizontal, you have to draw a new triangle to break up the force of gravity ultimately. And the real question, whether you've thought about it this way or not, and again, I'm going to back up and like detail this, but the real question that confuses people, even when they don't know this is what's confusing them sometimes, the real question is once I draw this new triangle and I try to like break up gravity, where in the new triangle is the one theta that I ever knew, like the theta that was measured in the horizontal of the lab? Because in my new triangle, like there doesn't seem to be any angle that's measured from a horizontal. Really, if you think about it, the question is where is the angle in my new component triangle? And I'm claiming it is, or I will be claiming that is as depicted in this picture. And if you really get that, if you understand why that choice is correct, then everything else follows. That's my punchline. I mean, it's not like a hilarious punchline. I mean, it's not like exciting, but and then we have to put in friction and all that. That's where my ship is heading. But let's back up and like look at this. Again, this is with the assumption that that you've been in the lab and that that you've experienced it. Now you're trying to write it up. I'm going to back up and I'm going to back up and uh explain it from step one. Okay, so I'm just putting that note in the chat again just in case. Okay, so we're okay. Okay. So the given, I'm just looking, changing the view of the screen. Again, there's a lot going on in this lab. I mean, there's angles, there's friction, and then there's like this prediction you're supposed to make, and then there's a result that occurs that I think is frequently counter to what most people would predict. And we'll get to all of that. But let's just start with the given is we've got some object that's flicked up an inclined plane. The inclined plane, I mean, in your case, it was a ball rolling. I don't understand that too, but let's just like whatever. It doesn't matter for the moment. So you got an object that's flicked up a slide at an initial angle. I'm sorry, at an initial speed of v naught. The angle is given as theta. The mass of the object, let's say, is m, or could be weighed in the mass. Could be put on a scale, an inertial balance, and called m. Um, and our ultimate. Okay, this thing is going to be flicked up and go up the plane. Then it's going to hit, that's going to run out of steam, stop momentarily, and come down the same plane, right? All the forces, whatever they are going to be the same forces. Like there's friction on this plane with some roughness, call it mu. We don't necessarily know the number. Just like there's some angle called theta. I don't know if we yet know the number, et cetera, et cetera. The thing is going to go up and then it's going to come down. And really, and I know in the lab, you predict like how much, like which is going to be faster going, which is going to take less time going up or coming down. We're going to talk about all that. But the general concept going on in this lab is the only way to make a prediction or to analyze the times going up and the time coming down is through the concept of acceleration. So really, if this were just a textbook problem, the first thing would be like, all right, given these facts of a block going up or a marble going up an inclined plane that's rough, what would be the acceleration up the inclined plane? And can we compare that to the acceleration that will occur when the object's coming down the inclined plane? Right? That's the situation. Our goal is to compute acceleration for each of the trips. Okay, so I'm going to look at the up trip first. Ah, okay, very quickly first, I draw a system schema, right? Whenever I'm analyzing anything, especially if I know my goal is to predict A of any situation, I do a system schema. I don't remember if you had to do this in your lab report or not, but I'm doing it. It's a system schema of the mass. So the mass and I'm doing that so that I can identify all the forces. And I'm analyzing all the forces for when I say I'm trying to predict the acceleration, I mean the acceleration at any given point during this experiment. When is during this experiment? The experiment begins, the stopwatch starts ticking the moment the ball is released from your hand, from the flick. In other words, the ball's right, it's given an initial velocity by your hand. So it's already in motion by the time the experiment, the data collection begins. So the moment that we're analyzing is some moment after your hand is no longer touching it. Stop me if that doesn't make sense. But so if I'm analyzing, if I'm doing a system schema for all the forces acting on the object, I'll even write. Okay, so now, so what force drag? Well, first of all, there's planet Earth because there always, the entire Earth because there always is. So there's that. Then I ask myself, what else is touching this object, this rolling ball? Well, the inclined plane is touching the object, the slide, whatever you want to call it, the surface, right? Okay. Is there anything else touching the object while it's moving, while it's accelerating, while it's slide? No, there isn't. My hand is not part of the experiment. How is my hand taken into account? It gave the object an initial velocity. If it didn't, if there hadn't been a hand, there wouldn't be an initial velocity. So it's taken into account, but it is not a force acting during the experiment. Therefore, so the only thing touching the object is the plane, and then there's Earth. So Earth always gets one line, system schema, right? The Earth is pulling the object. And then the plane is a surface that is underneath the surface of this object. It's easier to picture it as a block. In the lab, it was a marble, whatever, but there's two surfaces pressing against each other, right? And at least one of those surfaces is rough. You were told and and it is fun, it is important information in the lab that one of the surfaces is rough. The connect, therefore, there's two lines, right? I'm saying this is one of those situations where you have two surfaces pressing against each other. Therefore, they're going like this. That's one line of force, but they're also going like this. So that's the other line of force. So that's my system schema, right? For the lab, for lab 5. And by the way, I'm going to move on now. But by the way, I hope it's clear that would also be the system schema for the down trip. I'll say that, right? Because those are the only objects interacting with the ball in either trip. And the only thing difference between the up and down is direction, and system schemas don't care about direction. They're literally there to identify forces, right? So now we go to the pure free body diagram. This is always the procedure. We'll go to the up trip. So now every one of the lines in the system schema becomes an arrow in the pure free body diagram. That's the point of all this. Like I've now identified the objects that are interacting with my mass. Therefore, I've identified the forces acting on the mass. The whole point of this is not to invent fake forces or leave any forces out. And the fake force that most people would possibly invent in a situation like this is they might put the hand in and count it as a force. I get that, but it's wrong. Also, some people might invent something else like or some version of that. Like some people might say the motion up is a force because otherwise, how is it going up? It should be going down. But no, that's like not how physics work. I mean, I don't know how to. That's not a thing. So every one of those lines becomes an arrow in. It's not a thing because of Galileo's principle, which is why I emphasize Galileo's principle. So, like, things don't need help to move; they need help to change the way they're moving. So every one of the lines in the system schema becomes an arrow now in the free body diagram. But now I care about direction and the name of the force and all that. So I always go with the Earth one first. There's always mg down, right? Always. Then if I notice I've made this picture. This is like my step 1 DFP, right here. This is not a free body diagram nor a system schema or anything like that. That's a picture of the facts. But why do I need it in step 1? Because it's showing me like, oh, and I'll even add one more thing. Let's from now on, let's call. Well, I guess I'll get to that in a minute, actually. Hold on. But that's my picture. So it shows me, at least in the way that I did my lab, or I'm looking at this, my inclined plane went up, went up like that. I always do. As opposed to the other way. Like it shows me that my angle is to the left, not to the right. So I'm going to stay consistent with that through all of my diagrams. So now by the time I get to these diagrams, I'm already in step 4, right? Step 4A is a system schema. Step 4B is the pure free body diagram. So since the plane, I always, hold on, let me just invert the thing because this always happens. there's a way of doing this, right? Wait, let me just invert the video so every time I move my hand, it's if I can't remember how to do this, I won't mirror my video. Right. Okay. It's so strange, but okay. Um, right. So my plane was like that. So the normal force is necessarily like this. Like I'm gonna move on. But just to be clear, if someone were to ask, wait, is it okay? My normal force is going the other way. Is that okay? Well, it's okay as long if your picture is going the other way. Your original, if your inclined plane's going the other way, then it's okay. But you have to be, but only then. You have to be consistent with your inclined plane. I stop me if that doesn't make sense. Um, and then there's friction. Friction is perpendicular to the normal. Right now, in this case, the trip is up, the object is moving up. So friction is opposing it going down, right? This is my pure free body diagram for the up trip. Stop me if that doesn't make sense, but that's it, right? That's the pure free. There's nothing else in it, and nothing's been broken up yet or anything because it's the pure forces. That is the free body for any, and we're getting that to, like this would be in your lab report somewhere, presumably, if you're analyzing, if you're doing the lab. So that's for the up trip. To be clear, when the object is coming down, right? It's the same system schema, same forces. We still have gravity pulling down. We still have normal doing what, and I hope it's clear to everybody why normal. I mean, normal is at an angle, right? Because normal means literally how one surface is pushing against the other. Well, this whole thing is on a plane, so against means something tilted now. Stop me if that doesn't make sense. Okay, anyway, so that's the normal force now, but now the thing is coming down. So now friction would be pointing up. Right? So that's the key different. That's the key thing in this whole lab. Notice, I'm going to move on to the next step, but that's so annoying. Wait, how do I? Oh, lower my. Yeah, okay, okay. Um, what we're going to find, like, I know you know because you've been in the lab. The up trip does not take as much. Does not take the same amount of time as the down trip. That is already a surprise to many of us. Many of us might have expected the two trips to take the same amount of time. Many of, not all of us, many of us. I did like years ago. Um, because we're used to that. Certainly, if you throw something up, straight up in gravity and it comes back down, you should be aware that that takes the same amount of time. So it would not be a bad physics student if you expected these two trips to take the same amount of time. You're not a bad physics student at all. It means you've been paying attention to something for real. And further, if you even go further, you might be like, well, I mean, now I guess, I mean, now there's friction. So maybe it's not the same situation as just throwing something straight up, and there's an angle. But you might even then say correctly, well, but still, I mean, whatever the friction is, it's the same magnitude going up and going down. Correct. And gravity, the weight of the object is still the same going up and going down. Like you might still say everything is still symmetric just like when you go up and then down vertically, why is everything not symmetric here? Yes, we've now added friction, but we've added the same amount of friction, whether the thing is going up or going down. And that's true. All of that is true, which is not why this is an interesting lab. However, as you see right here, as you see right here, the direction of friction flips and nothing else flips. That's a key. I mean, that's a hint that something is not symmetric here. So let's keep going. If we're going to now really analyze the F's in order to predict the A, we go to the step 4C, the component free body diagram, right? We now need. So we're going to now have to break up some vector. Like we notice, sorry, I should say, we notice there are some vectors here that are not parallel nor perpendicular to each other. Like something is like off axis here. So something has to be broken up. Now, please stay. I know you're with me. I know because you're this. Oh, I'm sorry. There's something in the chat. Oh my God, I hate myself. No, I didn't say that. But that's a good question. Hold on. Okay, I'm gonna be really. So the question in the chat, totally a fair question for everybody. When drawing the FBD, is it okay for me to write gravity as capital F sub G, like force of gravity, instead of mg? Okay, that's actually I'm not gonna, that's a fair question, especially because I know many websites, and you're encouraged to get to get help, and we don't really use a textbook. You're using websites in the world to as a resource. And I know, yes, many websites and books will say F sub G for force of gravity. And similarly, whereas I always write N, they'll write F sub N, or I always write lowercase f for friction. They'll write capital F, lowercase f for friction. So the larger, and yes, whatever note, so the larger answers, and this is important for everybody because notation is important and it gets thicker and thicker for physics 204. If you find websites or sources that work for you and are making sense to you, and you use their notation because it makes sense to you, sure, as long as you use it consistently, self-consistently. Like if you're going to say F sub G equals gravity, then like do it every time. And maybe then for normal, say F sub N is normal, or tension, say F sub T. Like be consistent. You don't have to follow my exact notation. But the one thing I want to urge everybody, it is important, like for exams, stuff like that, just like with methods. You don't, if a method works, if it is a proper method and it works, or if a notation is proper and it works, it doesn't have to be mine. Hold on, someone's here. It doesn't have to be mine as long as it works and it's self-consistent. But like, even though you haven't seen this yet, and when you're doing an exam out, your job is to make it clear to me that I'm talking to everybody, not just the person who asked this question. I think it's a great question and they should get credit for it. But everybody, because I know, like, I'm one source for this material, but then you have to go to other sources to actually get it your way, of course. So ultimately, the way you get it is not necessarily my way, and that's fine. Notation can be different, methods can be different, as long as they're right and they work. But use a different method or a different notation if and only if it actually helps you understand it better. And that means that on the exam, you can explain better what you're doing, or you have a better ability to answer questions that like you hadn't thought about before the exam. It If you're using some other notation, and I don't think the person who's asking this, I know who they are. So I think that's why they're asking, like, because something else makes more sense to them than my way. Fine. But I'm cautioning everybody, when in doubt, like, don't take notation from websites or from other sources, like, just because they use those notations. Like, don't just memorize them or whatever. Like, really, what I'm saying is twofold. One, if you not that person, but all of you, if you take enough notation or things from other sources or from AI to the point where you never can translate back to my notation, to the point where you only understand it in those notations and you can't follow what I'm doing in class, that's really dangerous. You don't want to do that. It has to help you understand more so that you know what I'm saying. And so then on the exam, you can break it down in your way and make it clear to me, really. So in the end of the day, the optimum is that you follow both and that you're using some other notation to break it all down better back for me at the end of the day. Um, and and I will suggest to you that there are always reasons that I'm picking my notation. Like a lot of those websites stuff are not trying to teach, they're just trying to say the truth. I'm actually trying to explain it, trying. So I say MG to bring this full circle rather than FG, because MG is what I'm actually going to put in the equations. It will actually help me with the math. MG is what I'm going to plug into the left side of F net equals MA and get numbers from it. And it emphasizes that the force of gravity is really the mass times the free fall acceleration. If you know all of that and you're eventually going to write mg in the equation, say, yeah, sure, like do whatever system you want in the diagram. But eventually it's going to have to be mg. So there is a reason that I'm doing that. And to everybody else, and I will move on. But again, it's like an important to everybody else, whenever in doubt, when you find things on the web, if they don't look exactly like the way I'm doing, like assume that there is a reason I'm doing it the way I'm doing it, and you're going to want to cross reference until you get my way. You, I hope that makes sense. Like you don't just want to know some other way. You want to use some other way to then understand this class better. Because the other, I won't, I mean, there is like a whole AI like elephant in the room. And if you just, and I'm not, and I know who this person is, so I know this is not what they're saying. But I am saying when we start just taking things from AI and then just like doing them that way, and we don't cross-reference them to what's going on in the class, it's a dangerous practice. It signals things to me, like I can tell the difference. And it's not that it's illegal. It's not illegal, but it's just very risky because then I know the difference, and then like I'll just leave it at that. But okay. Just tell me if I answered the question. I'm gonna move on, but it's a fair question. It's an important question. But let me know if I answered it. But I'm gonna move on. Yeah, okay. Thank you. So you get points for the club. Okay. So what I have to do now is, sorry, that person's like, I'm never asking a question again. Are you kidding me? That was 15 minutes. I know. No, please don't come to that conclusion. Um, we have to now, so some of these forces are like not parallel or perpendicular to others. So forces have to get broken up now to the component diagram. Now, oh, so this is what I was right about to say before that question. Here's the thing. And again, I know that many of you have already like done all this already. You already like need, you've already been in the lab for 3 weeks doing this and you're already writing your report. So like a lot of this is all that. But now here comes a big step in this lab that a lot of people just got used to fast and memorized and possibly and don't know why they did what I'm about to say. And it's really important for physics 204, which is this. We're going to break some of these forces are not parallel or perpendicular to each other. Like, yeah, some of them have to be broken up into to make a component FBD. So what physics students tend to do at this moment is go, okay, which forces should I break up? I mean, that is in a way the right question. Which forces should I break up into like sine and cosine and all that, right? So something has to be broken up. So you might ask which force has to be broken up. Now, what I'm here to say, in order to answer that, which forces should be broken up, you actually have to back up and go do a step that people skip all the time. In order to know which forces, I mean, because the real answer is any forces could be broken up. Galileo. Like you could make any choice as long as you're self-consistent with it, and the laws will work. But some choices are going to be a lot more strategic, are going to cause you much less of a headache than other choices. So, in order to know, I'm here to say, and this is the lesson of today. What I'm about to say is the thing that ties together the conceptual thread of this course with the mathematical thread of this course. And it's the step that might have been, even if you got the right answer to this in the lab, you might not really know why, or to what I'm about to say. And you might have, so like I'm hoping it, actually, I'm just going to do, just give me an electronic sign or something if you're still like with me at all. Even if I'm driving you crazy. If you're like still okay, great. Oh, awesome. Oh my God, I love that. Okay, that's great. Thank you, Nadine. Thank you, Gabriella. Thank you, Jocelyn. Thank you, Rebecca. Thank you, Luna. That's a lot of people. Thank you. I love this class so much. I'm undeservedly, I don't deserve you as students. Okay, awesome, all of you. So don't decide what forces should I break up. Realize you're deciding to break forces into components that lie along axes. That's what you're trying to do, is break them into like X and Y pieces. So what you need to do, what we all need to do, is decide what is X and Y first. This is the Galileo point. We must first step back and say, what is my coordinate system? What perspective am I looking at this? Through what perspective am I looking at this situation? Right? And like, is my X and Y axis, and I know I mentioned this last week, well, I mentioned it every day, is the X and Y axis like this, or possibly is the X and Y axis like this? That will, the point is, either one would be correct. Like physics should be physics, whether you're looking at it like this or whether you're looking at it like this. But it might be a lot more convenient to look at it it might save a lot of computation to look at it one way rather than the other. So we first, always, in all of these problems, first choose, like consciously choose our coordinate system. And the way we do this is like the pro tip. This is a strategy. The way we choose, in other words, what are we going to make the x-axis? Like in all the previous problems, we called this the x-axis. But I have a certain feeling that maybe this time I should make this the x-axis, right? And yes, you should. And yes, that's what we did in the lab. But why? I mean, intuitively, you know why. But specifically, why? First, choose our coordinate system strategy. Okay, I think I mentioned this specific thing once last week. This will apply even to like pendulums and things where curves get involved and things get weird. This will like apply for the rest of your life, I'm saying, as a strategy. The strategy is you're going to choose a coordinate system, choose to line up the positive x-axis with the expected direction of acceleration. Whatever way you think the object's going to accelerate, not necessarily move, accelerate. Whichever way you think the object is going to accelerate, line up your x-axis with that. So, of course, that means in this case, just like you all sort of knew, oh, yeah, okay, the thing is on an inclined plane now, so I'm sort of tilting my head. I'm going to look at it this way. Yeah, that's what we're saying. Because the whole situation sort of tilted, we're going to tilt our coordinate system. But rigorously, literally, what I'm specifically saying, it's not just kind of like tilt our head, oh, I get it, the situation. I'm saying specifically, I believe that the ball is going to accelerate like that. So I'm going to call that my x-axis. Specifically, in this picture, I believe. Yeah. In my picture with the camera inverted and all that. Sorry, the mass. Okay, I'm looking at the time. Am I? Oh, okay. Oh, we've got a half hour. Okay, we could like talk about life. You know, I'm and here's something that some again, even if you've done this is a subtlety that some of you might not have. I'm saying whether we're well, I'll write it. Hold on. I'm saying I don't care. I don't care whether the ball is moving up or moving down. Either way, the ball is going to accelerate down and to the left, right? Like if you, this goes back to earlier physics now. If I throw something up in the air and it goes up, and then it comes down, it velocitizes up, then it velocitizes down, so to speak. But either way, it's always being pulled down, right? Either way, acceleration due to free fall always points down. Hence, when the ball's going up, it loses speed. And then on the way down, it gains speed, right? I mean, right? Same thing here. I don't care whether the ball is moving that way or moving that way. It's going to accelerate down the inclined plane. So I am going to, oh, and there's something in the chat. Awesome. I'm so relieved because, yeah, I'll get it in one sec. I'm just going to say, and then I'm saying then I'm going to tilt my whole coordinate system like this. So the x-axis lines up with the plane. And specifically, I'm saying along the plane in the downward direction is what I'm now calling from now on positive. Too excited. The positive x-axis. And then whatever's perpendicular to that is the y-axis, and technically I could call that positive or negative, but I'm keeping it like a right-handed coordinate system. Okay, so thank you. Okay, so I'm specifically saying now, and that positive part is where I got to admit, I'm partly saying tilt your axis so your x lines up with the plane. I know a lot of you sort of like already intuitively get that sort of, but I'm also saying down is positive, and this really affects your lab calculations. I'm totally going to go to the chat now and move on, but it's possible that you are a group who like gets what I'm saying and has like been doing a lot of work and stuff, but then somewhere somehow your numbers are not doing what like you feel like they're supposed to be doing or something. And one big reason possibly for that is that whether you and basically what I'm saying is don't change your signs or your sign assignment when you shift from an up analysis to a down analysis. The coordinate system is the same. Down is positive. Well, if you pick my choice, down is positive in both cases. You could pick another choice, but be consistent with it no matter what. Don't change. So don't make like gravity like negative in one case and positive in the other, which people do all the time. So that's something to note right here. I'm going to move on, but I'm going to look in the chat first. I'm also going to look at the time. Okay, chat. Hold on. I know one of it was a blessing me of. Yeah. Oh, oh, and it's in public. Thank you for going public. I really should open up a portal for people that have the guts to go public. Professor, and people that call me professor. Professor, if the vector lies along an axis, does that mean that it is one dimensional? For a minute, I think I see what you mean. Yes. If I think and bless you, Nadine, but bless you, Gabriella, for this question, and bless you, Nadine, for the blessing. Why do they call the Higgs boson the Pope particle? This is a joke. This is a stupid physics joke. You've heard of the Higgs boson? Okay. Why do they call the Higgs boson the Pope particle? Because it gives mass to the whole universe. Isn't that sweet? Okay. Um, um, if the vector lies along an axis, does that mean it's one dimensional? Yes. If what Gabrielle means by that question is if it lies along an axis, does that mean like we don't have to break it up into components? Yes. And that, by the way, Gabriella should also get points for please move forward. I don't know if she's just being polite, but okay, that question pushes me forward with this because what I'm saying now, so absolutely yes, if that's what you mean. I'm saying, okay, I'm really trying to say I will move on, but I just the problem is I've been doing this for too long, so like I know where people get. You don't need to hear this, but like people are always like, I don't know which one to make sine, I don't know which one to make cosine, or I don't know what things to break up or what. And I'm saying the real rule of thumb is don't ask yourself what should I break up right away. First, ask yourself what am I breaking it up into? What's my coordinate system? Well, this is the coordinate system now, x, y. Therefore, to Gabriella's point and everybody else, therefore, whoa, hello, emotional damage. Um, so yes, now I look at my picture I look at this or this picture, and now I see, aha, the normal force and the friction force are both along the axes that I've just assigned. Therefore, I think, and again, maybe Gabriella, you privately or publicly just tell me if like this is the point of your question. Like I'm saying, yes, the force, I mean, the friction vector and the normal force vector, they're fine. They're one dimensional, right? Now, in this coordinate system. So they don't have legs. They don't have components. That's correct. Only the mg has to be broken up now. Now let's take like really so okay, so in this case, in other words, okay, so this is the key now. This is why we break up mg. Please note, we've never broken up mg before. Furthermore, please note, mg looks like a vertical line. It looks exactly like something that you shouldn't have to break up, right? Again, don't skip over these thought processes. This is what your brain, many of our brains, when they first saw, when we first saw in the lab that like someone started, whether it was, Professor Liu or whomever, or a textbook or a website, when you first see that mg is like mg sine, mg cosine, please be honest with yourself and admit to yourself that when you first saw that, at least for 1 millisecond, your brain went, huh? I mean, mine certainly did, and it was a lot longer than a millisecond. When you first see mg sine and mg cosine, like, wait, what happened? Why did mg? Wait, why is mg being broken up? Now, the problem is that, and that's a really legitimate question. For many of us, we're such like science students. We're so intent. We've got life, and so we just like, oh, I don't know. The professor said so. Okay, just memorize it, move on. I'm here to say, don't do that, because then there's no way you can memorize yourself through physics. There's too much. But what you can do is stop and say, wait, that is confusing. What's up with that? What's up with that is, yes, it seems like gravity shouldn't be broken up because it seems like a vertical line. Since when do we break up vertical lines? The answer is we break them up when, when vertical is not along the axes. Our axes are not vertical and horizontal for this situation because the acceleration is neither vertical nor horizontal. So number one, so mg's off axis now. Hold on a second. mg is not an axis anymore. So I'm going to break it up. I'm going to zoom in on mg so I can resolve it, right? To break it up into components. And also notice when I do that now, and it's going to be a little bit harder than usual because like I don't know where the angle is, but also notice by breaking up mg here, well, first of all, we're breaking up one force instead of two. That's a huge advantage. And then also, I mean, we could do it the other way, but it's like a lot more work. I mean, in fact, you will, but it's a lot more eventually, but it's a lot more work. But the other thing is, the reason we're breaking up gravity is not only so that we don't have to break up the normal or the friction, but also so that we don't have to break up the A on the right side of F net equals MA. If we chose this coordinate system, then A is not aligned with any axes. So A will have a sine piece and a cosine piece. So the reason we're breaking up gravity into a sine piece and a cosine piece is to choose to do one kind of unexpected thing rather than three. I mean, to make one unexpected breakup instead of three. That's the point here. Breaking up is hard to do. Let's try to minimize the breakups. Like, right? Okay, so we're going to zoom in to the mg vector. Here's the mg vector. And now it has two pieces. It has one that, well, here, I'll do the other column. This is like now what's on the front of the board. It has one, Yahuba. One Like this is a triangle, right? This is a right triangle. Gra MG is now the hypotenuse. It has two perpendicular legs. One that's, like one that, sorry. Like, how did I know how to make those legs? Because those legs are lying along the axis um that I chose. This is negative y, that's positive x. You see what I'm, and they're perpendicular to each other, as components or axes should always be. Um, so one of those legs, this is now SOHCAHTOA, right? One of those legs is mg times sine of theta, and one is mg times cosine of theta. The question for many people, until they just memorize something that they saw in a book, is which one is which? Which one is sine and which one is cosine? And again, let me stop again and say, I know efficiency is not my strong. I know that for like 90% of what I've just said for the last hour, like many of you think you already knew 80% of it, and you're lying to yourself. You actually only knew 70, but whatever. But I know a lot of it is all old hat. But here again is the thing that most of us at some point are like, wait, which one is sine and which one is cosine? And it's a real question. It's welcome to the physics club. If your concern in life is, I know what's going on sort of, but I never know how people pick like which one is sine and which one is cosine. Yes, welcome to the physics club, but there is an answer. You would know which one is sine, and there's many ways to do this. One way you would know which one is sine and which one is cosine if you knew, like, if you knew which one of these two non-right angles was theta, right? The whole thing about SOHCAHTOA is that sine is opposite over hypotenuse and cosine is adjacent over the hypotenuse. And the whole thing about SOHCAHTOA is it's like opposite from the angle that you call theta or adjacent to the angle that you call theta. Really, if you remember, many of you, when you first learned SOHCAHTOA, your issue then might have been, wait, I get it, but like I never know which angle to actually pick. Right. It's the same issue. But so the answer here is the angle that you have to pick as theta has to be the angle that actually is theta. Like theta has to mean the same thing as it meant when it was given in the lab. It has to be the one theta that you ever measured or knew. In other words, like, where is that theta in this picture? That is the question. Of course, I'm going to answer it. But the reason I'm taking so long with this again is because I honestly believe that is the confusion that people have. And as long as you know that, as long as you admit it's confusing, we can resolve it together. But if you blow by it and just be like, accept it on faith, like sometimes maybe we do in other science courses, God forbid, or like, then then you won't get it. So let's admit it's actually a confusing issue. Where is theta in this triangle? And I'm going to tell you how to know, but there's something in the chat. Thank Quark that there's something in the chat. Hold on. That was the thing. Okay. You're welcome. Thank you. All right. Awesome. Okay. Still good. Wait, is that the same? And there are two Gabriels. Okay. Yeah. So how do I know which? So one of these two is theta. Like one of these two is the same, literally the same angle as was measured from the horizontal in the left. Wait, again, well, just raise your electronic hand if you get what the issue is that good. So, fine. Something in the chat. Thank God. Hold on. Oh, and good. Thank you, Gabriella and Nadine. Thank you. And Jocelyn, bless your souls and your quarks. If you're moving down left, how? Wait. This is a really good. Okay. This is a really good question in the direct chat. Also, I appreciate that this question in the direct chat is from like a new like all these different direct chat things that have been going on are like different people so that you all know. So I really appreciate that and you should all be giving yourself points. Like I do feel like I'm talking to a group here, so thank you. So this person is saying If we are moving down left, which actually, by the way, I'm not, well, we might be, but we also could be moving upright. I mean, we're accelerating down left. Let me just be clear. Like this, everything I'm saying right now could be true for the up trip or the down trip. But yes, we're accelerating down left. How come the X and Y vectors are toward the right now? That's a really good question, except I don't think they are. Wait, I, okay. Okay, I think I understand that. This is a, okay, so I'm going to back what this question is asking, I believe, is like, how did I even come up with my blue component vectors? And that's a really good question. I mean, yes, that's a really, maybe I should have said more, but hold on. Like, how did I come up with this? Tell me if that, I think that's what you're asking. How did I come up with these two vectors? So the answer is that when that components of a vector always add together to make that vector, literally. And the way we add vectors is we place them tip to tail. Like, bear with me for a second. I'm saying go back to regular unsurprising vectors from like displacement and lab 3 and stuff like that. If you walk southeast, if you have an arrow that shows southeast, what we're saying in physics is that's really the sum of two perpendicular vectors. You're walking some amount south, and then you're walking some amount east, right? So you draw an arrow that goes south, and then from its tip, you start the tail of an arrow that goes east. So south plus east equals southeast. And really it does. Meaning, now I don't mean, what I really mean is like in New York City, in Manhattan, if you want to get to a southeast location, you would walk south a number of blocks, like 61st to 60th to 59th to 58th or whatever. And then you would turn east and walk a number of avenues, right? Like 3rd Avenue, 2nd Avenue, whatever. And you would end up southeast. South plus east equals southeast. And the way you would draw that as vectors is you would literally make a south arrow, and from its tip, you would start the tail of an east arrow. Or you do it the other way around. Really, you might draw an east and then a south because addition is commutative. But, right? So, and this is to everybody. I think this is a very important question because this does confuse people. When we draw the components, when we resolve a vector into its components, its two components are always perpendicular and they're always adding together to make the final vector. So they're always placed tip to tail. So now if you look at this, and I'm really the person who's asking me this is a real question. This is really on point if I'm understanding. So I'm really going to ask that person when I'm done to tell me privately, like, and I'll ask anybody to tell me privately whether I've answered this or not. Because if you look at the picture now, yes, which really throws people, you've never seen a picture like this before because I'm suddenly resolving a vertical line. But gravity pointing down. What I'm saying is to point down for a marble to be pulled down while it's on a slide that's going like that really means that it's being pulled in two directions at the same time. It's being pulled it's being pulled to some extent down left, plus it's being pulled down right. Like I'm saying, in the same way that south plus east equals southeast, I'm saying down left plus down right equals down, physically meaning when the earth pulls straight down on this ball, it's really because the ball is on a slide, the earth pulling straight down is really accomplishing two tasks. One task is it's sending the ball along the plane, that's down left. But the other thing is it's holding it against the plane. It's like keeping it from floating off the plane. So it's yanking it into the plane, against the plane. That's down right. So I'll erase this. So like this thing here is down left, like that's gravity. Gravity's doing two jobs. It's sending the ball along the plane, but it's also keeping the ball on the plane, into the plane, against the plane. So I'm saying down left plus down right equals down. Does just like south, and literally they're tip to tail. Like there's if I drew the arrows any other way, this wouldn't work. I mean, could I draw them on the other? No, I couldn't draw them on. Like this is the only way this works. If the inclined plane is the way we're visualizing, like gravity is to some extent shoving the ball along the plane, and to some extent it's shoving it into the plane, keeping it on the plane. I want to look. Please, I think it's a really good question. Hold on, I'm going to erase this. I want to pause for a second. Most particularly that person who just asked the question, could you tell me in the chat if that did anything for, but also maybe anybody else, if that explanation made any sense to you? Hold on, I'm just looking in the chat. Wait, oh, for real? Okay, and you're not being polite. Okay, thank you. I appreciate it. I hope. But, okay, no, thank you, thank you. I think it's a really good question. If I understood it correct, and you should follow up later, like email it to if it didn't. But anyway, okay. So that's my picture. Now, what time? I know we have 8 minutes. Okay, that's my picture. If I know, so one of these angles, either that top angle or that bottom angle, is theta, and it's not arbitrary. I'm not just saying theta like to mean X, like unknown angle. No, I mean specifically the original angle that we know from the lab. One of these two angles is that original angle from the lab. Okay, the question is which one? Now, um, uh, uh, well, so the question is which one? Well, how do I know? The most straightforward, I think it's the top one. How do I know that? There's many ways I can know, but I think the most straightforward way to answer this is picture picture this horizontal line here. Here's the lab table, right? Not the inclined plane, but the horizontal lab table, right? Then, then sorry, I mean, I don't think it's the top one. I think it's the bottom one. Oh God, did I even draw it wrong in the original page? Holy crow. Hold on one second. If I drew it wrong in the original page, that's second, let's just read. No, sorry. Oh my God. You might want to, I'm making a correct. Go back to the original page of this whole PDF or whatever. I meant to put the angle down at the bottom. And my God, maybe that's why you've been paying attention the whole time. Because you're like, wait, what? That's totally not what I thought. I mean the bottom one. And I'm going to show you now why. Okay, so wait, just raise your hand if you just caught that correction. Okay, that's good enough for me. That's one person. Thank you. Okay, so thank you, Gabrielle. All right, so here's why. Can't believe all this talk, and I thank God I didn't get to that yet. All right, here we go. Because look, the original angle in the lab, is right here. Ah, oh my God, what just happened? Did I just lose all the P? It's a good thing this is not actually a movie because boy, have I killed the suspense. Okay, this angle is the original angle in the lab, right? Well, if that's the angle in the lab and this is a right angle, which it is, then then this top angle must be the complement, must be 90 minus theta, right? Which means it's the other one and similarly, this must be 90 minus theta. So this is theta. I mean, because all angles of a triangle have to add up to 180. I mean, that's one way to see it, that this angle down here must be theta. There's other ways to see it too, but since we only have 5 minutes, I'm going to leave it at that for the moment. Like, wait, raise your hand if that makes sense. That's one. Good. I appreciate it, Gabriella. Is anybody else? That's okay. That's three. Okay. And the control of the experiment, we have 5 minutes left. Just raise your hand if you're paying attention to me at all at this moment, if you're with me at all. Like even okay. Okay. Thank you. I can't actually see. Oh, Jocelyn, thank you. Lunar, thank you. Okay. So if that, if that angle to the side is theta, then the angle to the bottom is theta. I mean, it is that simple. So simple that I shouldn't have written it. It's that simple once you No, it's a real, like everything in physics, the answer to the question is really simple as long as you ask the right question. The issue is, can we be honest enough and clear enough to get to the right question? So I think that angle down below is theta. So what does that mean now? It means if I look at it, then the vector across opposite that angle, like this is opposite then. So this must take sine. And this is adjacent, so this must take cosine. It's that straightforward once you actually, right? But don't be fooled. It's that then if you say, well, why did we just spend an hour and 20 minutes on that? Because we had to get to the point of seeing that that's the question that we needed to ask in order to get that answer. But if we ask that question, we're now saying with 4 minutes left, we're saying, fine, if you have mg like this in this coordinate system, then that is mg sine, and that is mg cosine. So therefore, now we can make a component free body diagram with 3 minutes left. Then the component diagram becomes for the up trip, like we now, the whole point of a component diagram is you get rid of the original vector that was off axis and you substitute in its components. The two components together are accomplishing the same job as the original vector. Earth thinks it's just pulling your object straight down, but you've put your object on a slide. So by Earth pulling it straight down, what it's really doing is pulling it along the slide and at the same time pulling it into the slide. And each one of those pulls is less than the total. Each one is a fraction that they're adding together. Sine and cosine are fractions, right? So the diagram now is we don't have mg in it anymore. This is also why I like to write mg rather than fg because it doesn't matter. But so now this is mg sine. This is mg, and notice I just copied, right? I'm literally just copying those arrows directly into my out of my zoom in, like this was theta. I copy them out into the free body diagram, and normal is this Gabriella's point, normal is unchanged. And if we're going up, then friction is pointing down. So that's friction. That's the up picture, as you know from the lab, but that's why. That is the diagram of forces for the up pick for when the ball is moving up. When it's moving down, the picture looks like this. Still mg to mg cosine, mg cosine. I just copied it straight from my resolution picture. Sorry. Normal, but now if the thing is on its way down, then friction points up. So now sorry, it was 1 minute left, Angel, but that's my point, is that the friction flipped. Everything else stayed the same, the friction flipped. That makes all the difference in F net equals ma, and therefore the A. Okay, Angel, sorry, go. Or I think Angel has her hand up. Sorry. Or was that just from before? Angel, your hand is up, I think, and we're 1 minute left. Go for it if you have a question. Wait, no? Okay. Going once, or maybe you're on mute. You are on mute. Do you have a question? I know there's only 1 minute. Well, okay. If you do, you get to hang out after class for a second. But therefore, I'm just right. So therefore, the up trip is mg sine theta plus f equals ma, and the down trip is mg. And notice my positive and negative signs. Mg sine theta is positive in both cases because down I made positive. But in one case, mg is working with the friction. In the other case, it's working against the friction. That makes all the difference in the calculations and the predictions. We'll continue that on Wednesday, obviously. Okay, but we're done. You are a wonderful class. I can't thank you enough. Seriously, I'm going to stop the recording. But Angel, if you do have a question, you're welcome to ask it right now, or anybody. Okay, bye. Or Nadine. Great. Okay. Have a good day. Yes, I'm stopping the recording.